Welcome everyone, thank you for connecting, and I believe today's meeting will be pleasant and positive experience. Let me make everyone a co-host so that if needed you can share video. I believe everyone is co-host now. So what is the if you have received an email with materials for this meeting, please do not wait for me too much. Just download MATLAB scripts and run them one after another. So I'm not going to offer anything really smart. I will just give some comments how to interpret this codes, and I'm very confident it will help our progress in the class material. So as we go, we may test one technology, the Zoom whiteboards, so that we can try cooperatively write on the analog of Blackboard, whiteboard. In the previous lab, we basically completed conversion into rotating frame or into the interacting picture, and we did discover that the modeling of two-level system interacting with the oscillatory perturbation behaves much healthier, much more reliable in the rotating frame, in the interacting picture. Specifically, their Hamiltonian becomes time independent, and simulation are less sensitive to, details of the parameters, to the size of the time step. In the lecture, in the class material yesterday, we did started a so-called pulse area theorem that tells that the degree of oscillations between ground and excited states is very forgiving. It is not much depending on the details of radiation, but it depends on the envelope function of the oscillatory radiation, and it depends on the area under the pulse envelope. So we may want to implement these ideas into subsequent improvement of the code that we were working on. And why should we waste time? Why should we invest effort into these changes? The goal is to arrive to the stage. There is a dual goal. One goal is arrive to the stage when we can convert from abstract mathematical models to something that can be at least hypothetically compared to experiment. And this comparison to experiment will be spin echo in the nuclear magnetic resonance. So we want to mimic by mathematical, computational, theoretical modeling, you should mimic the environment of single spin 1/2 and see what happens when it is being perturbed by external radiation. There is a situation, there is an objective fact that the treatment of spin 1/2 and any two-level system is mathematically equivalent. It will be covered in the lectures, but we will use this fact. And when treating models mathematically, it is absolutely equivalent whether we describe electronic levels like comma and luma under optical field, or we use megahertz microwave range splitting of nuclear magnetic spin and explore spin flips. There are different time scales. There are different experimental setups to measure it, but mathematically it's not similar, it is identical. Okay. Let me, before we go to scripts, and again, everyone is welcome to start scripts and check what is going on in the subsequent order, like 2, 3, and then 3 is moving. But before we go focus all together on them, let's check if you can practice the technology of whiteboard. And if it fails, I will just open the an analog as yesterday for the lecture to draw some equations. And I'm going to click a button whiteboards on the Zoom. And let me ask if you can see this board and if you can write on it. So if you can, please just make some annotations, some marks, and do not hesitate to do just little things. Yes, exactly, like smiling face or stuff like that.
I see no whiteboard right now.
Okay. Do you see this whiteboard when I see Tori, Adam, David, Patricia? So at the bottom of the navigation panel of the Zoom, there is a second from right, there is a button whiteboards.
I do not have that button. I have breakout rooms.
There is a, do you see like 3 dots that tell more?
No.
Okay. Do you see what we are doing all together now? Because I see a lot of fun. Steven is here.
I do not.
When was the last time you updated Zoom?
Yeah, it's I don't think that I have updated it on this laptop since I got it on here. Is it like a new feature?
It's a newer feature, yeah.
Oh, okay. I might need to update Zoom then. I will log off, try to update Zoom, and then we'll see if that fixes it.
Okay. Okay. Yeah. Thank you. And I hope very much everything will be recorded. So if there will be something really important, you will not miss it.
All right. See you in a bit.
Okay. So before we go forward, let me invite, I don't know how to make it an organized effort. It's very democratic. You can select like a range of the board, which will be like your part, so that we do not need to coordinate. Like I can write something in this area, and anyone can select a little area and just write some little things. So please try to select a little area where you would feel comfortable and try to reproduce the spin operators. Like I already provided SX. please do SY and SZ.
Like everyone?
Yes, yes. I really, it looks like a computer game with many players, many characters moving around this arcade game. So it's very dynamic, and I hope everyone has fun. Okay, I see David did has written the SY. Okay. Hadassah is writing SX. Okay. SX is reproduced. And now Adam and David are writing SZ. And okay. Okay. So yeah, David did it quicker than others. Now the next little exercise. Please try to write down the expression for expectation value. So if you do have the quantum state of this two-level system as superposition of, let's say, C1 for state down and C2 for state up. Now we do need for this class to know how to find the expectation value of SX, expectation value of SY, and expectation value of SZ. And please, oh yeah, if anyone, I don't know how to vote. If you have an idea how to do it, just try doing. If anyone has doubts, please give me like a feedback by typing or saying by voice, so that I give additional comments. I think no one gives. Oh, the board is really good. Oh, it is much bigger. Oh, there is something hidden that I didn't notice. Okay, so it's a really big board. Okay, okay. SX, SY, Z, Adam, David, Tori, yeah, Hadassah. As of now, I do see very healthy attitude from Hadassah. So Hadassah, would you please, everyone please continue, but may I ask Hadassah to just give verbal explanation of what you're doing through the microphone.
I'm doing it the multiplication of matrix form, since, and I'm assuming that we're in the SZ state, so I guess whatever the SC eigenvector is multiplied onto the SX matrix and then again with the other.
Okay. Okay.
Eigenvector.
So, let me interpret that you are doing bra, then operator, and then cat, right?
Yeah.
Okay. And do you plan to continue and write down what would come out of this.
I mean, if we're in the SZ basis, I think if I remember right, it's like they're gonna be
So,
spin up or spin down, since we're measuring in SC, and with SX, it could be up or down, but
and I believe in what in Hadassah notation there should be for bra when needs to do complex conjugates, right?
Yeah.
Okay. So please I invite and encourage everyone to try continuing this exercise on his or her part of the board. Landon, do you see this whiteboard now? Oh yeah, I see.
Yes.
Okay.
It's
So just select maybe a little portion of this board where you'll be doing your exercise and go ahead. We are trying to write down an expression for expectation value of Sx, Sy, Z in case we do know the state function. I didn't expect it will be so much fun.
well, I can write on it, so that's good.
Okay. And I recently discovered that one can zoom in and zoom out by focusing on different areas. It's a very big board. I do see writing of Stephen. So let me add a comment. So Stephen, you're answering that SZ can be either plus or minus H bar over 2. So there is a little confusion. Those are eigenstates of a Z operator, and it will be H bar over 2 if it is with guarantee the state up, and it will be H bar minus H bar over 2 if it is with guarantee state down. But the question is, what if these coefficients C1 and C2 are not zeros and ones? What if they are like proportions for something like C1 equals C2 equals equals to 1 over square root of 2. So if the system is in a superposition, in a superpositional state, what would be the SZ projection for such state? So let's we need to design the answer for each expectation value of each spin operator for this situation. So I do see so TO is Tori. I see, yes, I see. I see Hadassah. I see Adam. Okay. Adam did. I don't see yet answer. I see reasonable effort. I see Max. Yeah. If you are done with SX, please continue for SY and SZ. I see Patricia. So Patricia admitted to assume that Planck's constant is 1, which is okay for atomic system. And some people don't care about factor 1 over 2. It's we'll fix it later. Okay, let me see. Okay. So David is using Dirac notations for everything, but then the operator Sx also should be if you want this thing, Sx should be in direct notation, something like still h bar over 2, and then converting plus into minus, and plus converting minus into plus. Okay. It looks like Patricia is quicker than everyone, and she just skipped the factors, and it helped her to be quicker. So Max, I believe no, you're doing right. No critical comments. Everything is correct. Mm-hmm. Okay. Tori, I wonder if the sign here for SY should be plus. I would double check, because in the operator there is a minus here, and it may reflect into sign in the final answer. Okay, I do see that Max has completed everything. Let me check. Okay, I do see that Hadassah is approaching. Yeah, and Patricia was very quick. So I believe Max and Patricia did it in the quickest way. Okay. So yeah, I see Adam has Adam, do you have, what is the sign? Oh yeah, you moved for yes, for minus for Z. Yes, that's right. So I'm very happy, and I see very healthy progress, so that everyone is getting in the right direction. And please, no, I think everyone understands what we are doing. So the answer, and I'm not picking anyone specifically for an example. I just see it with bigger font for Patricia right here, and I do see it for Max. So as soon as we do have expansion coefficients of the quantum state, we can express expectation values, right, by practicing Bryant-Cat. And what is important that expectation values include summation of products of the expansion coefficients. So all operators are composed of pairs of pairs of expansion coefficients. So now, what is our goal? We do have a code that uses all these advanced methods, interacting picture or rotating frame. It has the light to electromagnetic to matter interaction, and then we do have coefficients C1, C2 as function over time. We do want to program result of any simulation by converting these two pair of coefficients into Sx, Sy, Sz as function of time. And you do see how, well, you did it yourself, how it can be converted. So this is something that each of us can program independently. The codes are shared, it is not needed, but I believe everyone understands how it is going, right? So dynamical simulation are converted into the expectation values of operators. If we speak about NMR, EPR, or EPR, we will call that it is a spin, a doublet for spin 1/2. If we speak about electronic transitions between HOMO and LUMO, we will just tell that it is a pseudo spin. So even if we have a single transition, math for two-level system is identical to math for a spin. Now, in the previous version of code, our perturbing Hamiltonian in the Schrödinger picture was dipole times electric field amplitude times cosine omega t. And after we admitted resonance condition that h bar omega is very close to E state 2 minus state 1 energy difference, and we moved into interacting or rotating frame, the Hamiltonian became time independent, minus mu E, and the Hamiltonian in rotating frame, if you write it as operator, as a matrix, was there was a 0 on the main diagonal and just dipole times amplitude of electric field on the off diagonal. So we are considering situation when the electric field is slowly changing its amplitude. So instead of being constant, we will have it slowly growing and then slowly falling, so that it will be a pulse. So the event of interaction with electromagnetic radiation, and we can tell that it is in rotating, or that we already took into account the oscillations. And we look only for the envelope. So we anticipate that the quantum state psi will evolve in time as cosine theta state 1. And those are theoretical considerations, but the simulations will be very similar. So sine theta state 2, where theta is depends on time, and it is integral from minus infinity to time t of dipole electric field envelope as function of tau d tau. So we do want to, why do we want this little exercise? Because the set up experiments typically operate with pulses, and if you have experience or a little exposure to NMR, you also know that it is most of NMR experiments are done with pulses. I believe Stephen will teach us more in a week and 1 day from now about pulse NMR, but we do need this tool. So pulse area theorem applied to two-level system. We do want to be universal and be able to describe not a single pulse, but maybe several of those, like a train of pulses. And most reasonable shape of the pulse would be to just assume that it is a Gaussian curve. So center time when the pulse is centered. Let's put it like t center minus t squared, and then some width parameter and some normalization. So the electric field envelope, so we already got rid of fast oscillation, depends on time as Gaussian function. So it is the goal to program this event. So this is input. And the stuff that everyone so gloriously derived for expectation values of Sx, Sy, and Z are output. So we do not plan to write the code from scratch. We will borrow what we used on previous two labs and just slightly modify the code to describe this new setup. So I'm going to exit whiteboard. I hope it will be kept so that we can later look on it if needed. And then I'm going to share screen and demonstrate my MATLAB window. I'll do some comments on the scripts, and then if needed, we'll interview one by one and ask everyone to run the code and share screen as we see it needed. So please prepare to the event, to me leaving the whiteboard. I don't know if it will affect everyone or you can continue there. Maybe if I click on close whiteboard, it may close access for everyone. Maybe not. I'm doing it for the first time. So are there any objections against closing whiteboard? Okay, no one is speaking. I'm pushing the button close whiteboard. Okay, and now I'm going to share screen and go into the MATLAB window. So there are 3 codes. Rabi rotated in rotational frame 2, Rabi 3, and Rabi 3 with movie. So if I'm going to let's create new figure. Create new figure. And just launch the Ravi Rot 2. So it has been completed very quickly. I believe you can run and see this image on your own. So this version 2 of the script has a change compared to what we saw and what we practiced last time. So the yellow thing at the bottom near the x-axis represents electric field as function of time. You see it oscillates with very high frequency, but then it does have a very slow envelope function. And we do see more than one pulse. We have 1, 2, 3, 4, 5 pulses in this window. Blue and red lines correspond to population of the ground and excited state. So what we see that originally, before pulse has arrived, the ground state is populated with 100%, blue line, and then at a time of a pulse, they start to change as prescribed by pulse area theorem or Rabi oscillation. So the population of ground state drops towards 0, and population of excited state increases simultaneously. This simulation is set up to have the area of the pulse exactly or very close to the situation when it is equivalent to 1/2 of Rabi cycle, so that it performs the one spin fluid or one event of excitation or de-excitation. Then at a time when electric field is not oscillating, when the envelope function is 0, system remains in where it was left. So the population of ground state is 0, population of excited state is 100%. Then at a certain time, we do have second pi pulse. And then we see that population of excited state is experiencing this 1/2 of Rabi oscillation. So it drops from 100% to 0. And at the same time, the population of the ground state grows to 1. So I plan to focus on the code and give some little comments. If you think it is boring and not needed, let me know. I'm just trying to be meticulous and so that we have all doors open. But if you think it is not needed, we can speed up time. So maybe I can stop sharing and request voting. So if you approve me mumbling a little bit more about structure of the code, please vote with, okay, 2, 3, 4, 5, 6. Okay, majority. Even if couple of people. Thank you. Okay, let's do 2. Sure. Okay. So the most important part of the code is, so it is inherited from what we did last time, is setting up the Hamiltonian and setting up evolution operator and making evolution like time step forward. We did so big effort to make Hamiltonian time independent, but now we it's our time to make it time dependent again. So right now, this Hamiltonian is next line is Hamiltonian in the rotating frame / interaction picture. So we do have zeros on the main diagonal. In fact, if one wants to be very meticulous, if we going far off resonant, main diagonal should have this detuning parameter. So delta over 2 plus in bottom and with plus and with minus. Delta over 2, where delta is exactly this subtraction of frequency and energy difference. But right now the code is set up in exact resonance or very close to resonance, so we can not focus on it at this time. So the off-diagonal elements include subtraction. We already applied rotating frame and rotating wave approximation. So the subtraction of frequency and energy difference. So it shows phase accumulation, which would be needed generally, but in the resonance condition, they cancel each other, and this exponential here and there will be zero. I will be back in a very quick minute. It isn't. Okay, I apologize for this little break. Returning back to the discussion. So this exponential will be equal to 1. The parameter v gives us the parameter for amplitude of transition dipole times electric field, and this f has a meaning of envelope function. So let's maybe label it as f and the lobe for several pulses. So you see current version of time minus, so the variable pulse is the time when pulse is happening. Maybe variable pulse, center of each of specific pulse, center time of specific time pulse. So here we do make a little preparations so that there are total 16 pulses, and they are set up to be away from each other by this much, and they start away from the center. So by practicing this f plus this Gaussian function expression, one adds together several pulses, but and it is done at each point of time. When we come to specific match between value of time and the designated center of pulse, the certain exponential certain part in this summation will give maximal contribution. Okay. Okay, I think this is one important part, and as we go forward in evolution, we record wave function, we accumulate wave function at each point of time. Okay, so after the cycle over time has been completed, we need to process output and prepare the something to plot. So when the code was working, it didn't plot SX, SY, SZ. It showed only populations, but you can see that it is all psi component number one with conjugated all psi component number one. This would correspond to C1 star to the power of star times C1, which is population of state 1 over T. Here we do have conjugated of C second component, C2 conjugated times C2, which is population of state 2 over time. Next, 3 lines summarize what you have done in our whiteboard experiment. So let me add comments. So this line 58, I know that if I add comments, number of lines changes, but line 58 tells that we have here conjugated of C1 star times C2, and then we add conjugated C2 to the power star times C1. So this is what Patricia did at the beginning. So we can tell that it is SX, but dimensionless. So if it would be SX divided by H bar and multiplied by 2. In the same way, the next non-comment line will be it is multiplied by imaginary unit, right? So here is I is imaginary unit defined at the beginning. Here we have minus sign. Here we have another imaginary unit. And then it will be projection SY. And by subtracting population of upper state minus population of the first state over 2, this would correspond to so Max wrote in shorthand notation C2 squared minus C1 squared. If so, it is equals to SZ. Currently without 2 divided by 2. So it is SZ divided by H bar. In the literature, especially in the literature about making analogy between electronic and spin degrees of freedom with the same mass, this analog of SZ expectation value is referred to as population inversion. So if population of excited state is bigger than population of the ground state, it means we have inversion. If it is everything in ground, then it is normal. Okay, and at the end, one is plotting the dimensionless time population of ground excited oscillating function times this envelope function, and just enjoys, right? We can use copy paste of this command and so instead of plotting the P1, P2, we can write down these variables that were defined as Px, Py, Pz. X, P, Y, so I think this makes all of us a little bit scared of having too much information, but to understand what is what, we can use, let's do Px dashes. Dashes. Okay, better. So Px with dashes and Py, let's do it with dots. And then Pz, let's keep it solid and do it maybe color red, green, blue. So red will be Px, green will be Py, and blue will be Pz. Maybe I'm going too quick. Let me stop sharing for a second and ask if there are questions, or should I be quicker or slower like a little feedback. At least please vote if it makes sense, or vote negatively if it doesn't make sense, if I need to stop and explain or change the subject. Okay,
could I see your command window, please?
Yes, yes. Thank you for voting in approval. Do you see the command window?
Yes, thank you.
Okay. So how to interpret what we get? So the population inversion starts with -1/2, since we divided by Planck constant, and during the time when pulse is active, it flips to the, like, from ground to excited, and then during the second pulse it flips from excited to the ground. The SX and SY, or their dimensionless analogs, are zeros when pulses are not applied. When the pulse is active, they are raising, but when pulse is gone, they're returning to the value close to 0. So in this sense, one can interpret that SX and SY are quantitative measure of transitions. So if transitions are happening, SX and SY are non-zero. So please express your concerns or questions, if any. And I'm going to stop sharing for a second to check for the feedback, if anything is typed. So I'm going to move to the next code and see what happens. The rest of the meeting will be a little quicker because we went over major aspects, and it should be good. Desktop 2, share. Okay, so if I select the Rabi underscore rotated 3 in the command line, I can clear everything just in case, and then run this rotated 3. So basically it does the same thing as we have already discussed, right? And in addition, it brings a figure that shows the trajectory of these 3 components on a surface of a sphere. So the 3 numbers, S, X, SY, and SZ, can be analyzed as a vector starting at origin and pointing direction somewhere in the space. There is a way to prove that if spin 1/2 or pseudo spin for Como and Fuma is isolated, if we didn't bring in thermal equilibrium and we didn't bring average over ensemble, then this vector connecting the origin, this vector will have a constant length, and vector moving randomly on some law, but keeping the same length would correspond to Sx squared plus Sy squared plus Sz squared equals constant. I believe you had it in the first part of the course. So this is referred to as Bloch vector, and state of 2-level system can be mapped to a point on a surface of a sphere. Please, I'm going to stop sharing and check once again if this idea of mapping a state of two-level system or a spin onto a surface of a sphere sounds normal and acceptable, or anyone wants to oppose. So we did compute it at each point of time. We compute expectation values of three pseudo spin projections as x, as y, as z. Each of these projections include products of two expansion coefficients and summation of these two products. And these three numbers indicate a point on a sphere of radius h bar squared times 3/4. Let me ask for any feedback, comments, criticism, or an approval.
So, okay, so like the SZ in this case is basically like excited state population minus ground state population.
Exactly. Yes, yes, you're correct.
And then SX and SY are sort of like the transition currently happening between your states.
I cannot express it better. So they are quantitative indication of transition happening at a given time.
So, like, what's the difference between SX and SY then?
Because of the dimensionality of the system, like to have a complete set, one needs there are three independent projections. So it is just nature of the system, because so it's on one hand, it's just mathematical property. The two-level system is two complex numbers, so like four independent coefficients, and one needs to, for unambiguous mapping of the spin state onto real spin state, which is complex, onto real space, one needs three projections, not two. So it's if it would be a math course and if I would be prepared better, there could be theorems and logical consequences that to map state of a spin into real space, which is better for us humans, two complex numbers for this situation can be mapped on three real numbers. So it's not a proof, it's only direction of thought.
Right, because it's more complex than like basically just saying like SX is like ground to excited state transition and SY is the other way around.
No. Okay. So I did a comment in reply to your question from mathematical point of view, now from physical and natural point of view. It will be not a clear answer, but it will show a direction of thought. So experiments and concept of magnetization was introduced before, well, not, and NMR was introduced after advent of quantum mechanics, but understanding that magnetization can have three projections was quite clear for a couple of centuries, right?
Yes.
So, and to indicate direction of magnetic dipole or a coil with a current, one needs three coordinates.
Yeah.
Because we live in three-dimensional space. And later on, one was able to establish connection between state of doublet of spin, which is indicated by two complex coefficients, and three projections of magnetization. So by adding together multiple systems, multiple doublets with having the same quantum state, their corresponding magnetizations, their corresponding projections, like angular momentum, add together through these coefficients from gyromagnetic ratio and create macroscopic magnetization, which needs 3 components. So SZ is a projection of magnetization onto the axis defined by constant, static, time-independent component of external magnetic field, like the one that creates Zeeman splitting. And SX and SY are 2 other components which are perpendicular to SZ direction. And the way to live with it is just to accept that our space is 3-dimensional, and if you have a selected axis SZ, then there are 2 linearly independent vectors which are orthogonal to SZ. I'm not telling you it is a full answer to a question, but please provide a feedback if it gives a little piece or some directions of thoughts.
Yeah, I'm just trying to kind of get like an intuitive feeling for like what SZ, or sorry, what SX and SY are.
To get an intuitive feeling of what SX and SY are will be a goal of next 2 lectures, the one tomorrow and the one on coming Tuesday. So we will be not left alone with spin as of today. There will be additional discussions. But if you want a quick answer to address the curiosity, and me jumping ahead of class material, if we explore this, if we explore the sphere, right, then anything that may happen with spin or pseudospin is a journey on the surface of a globe, right?
Mm-hmm.
So the motion between North and South Pole corresponds to change of the population inversion, to change of the SZ projection, which we can interpret. And the motion between X and Y on the equatorial motion does correspond to quantum phase accumulation. Like any wave function accumulates phase as it goes forward in time, proportional to energy difference, and then just so it is the interpretation of the motion in SX and SY plane. On one hand, it is a phase accumulation. On another account, this is very much analogous to oscillations in phase space between position and momentum. Like SX and SY are conjugated variables similar to position and momentum for harmonic oscillator. We cannot practice oscillation of position without momentum being changed. They just by matter of fact, they are connected to each other, because if position is changing over time, we have different momentum. So the relation between SX and SY are very much similar to relations between position and momentum. And this equatorial motion is very much similar to motion in phase space if we look on harmonic oscillator and make one axis X, another P, and then oscillations will be a circle in a phase space. London, does it sound reasonable?
Yeah, as far as I can tell.
Okay, yeah, thank you. So if there are no, I'm very happy, I'm grateful for questions, and let's go forward with the codes. I'm going to share screen once again. Just look two. So this code is very much similar to the one we already did. Some changes are done in optimizing, in writing this expectation values in a more elegant way. So instead of extracting components, one can literally practice bra operator here. And to practice this bra times ket operation, we already have, so psi with prime means that we convert column to the row and do conjugation automatically. And to practice this thing, we do need to define Sx, Sy, and Sz before we go for simulations. And it can be done in the following way. So creation and annihilation operators S minus, S plus, which are conjugate to each other, unit operator, and then Sz are S plus, S minus, minus, S minus, S plus, and Sx are summation of these operators, and Sy is subtraction of this operator. Indeed, if you do believe that Sx is, Sx is a matrix with 0, 1, 1, 0, right? With factors Planck constant and over 2, then adding together matrix Sm and matrix S plus, which will be just flipping it over the main diagonal, will literally reproduce this matrix Sx with 2 positive real off diagonals. In the same way, if we subtract the things here, we will reproduce the situation of 0, I minus I 0. And as being too excited right now, I can put minus in the wrong spot. But we can define operators ahead of time and then practice them. So just to show that they are defined, we can type Sx, Sy, and Sz. So they are defined in assumption that Planck constant is equal 1, since we are doing stuff in atomic units. So Sx is real, Sz is real, and Sy is imaginary. So it has 0 real part and non-zero imaginary part. Back. So the rest of the code is the same. We inherit this train of pulses. We put this Hamiltonian evolution operator, and then at each point of time, we accumulate, we compute expectation values of these projections, and then accumulate them in the trajectory matrix, trajectory array. For time dependence. Okay, and at the end, we can do 2 plots. One is plotting Sx, Sy, Sz, and another plot. So the command figure brings in new panel, and then we can just plot sphere with some, so this alpha 0.1 is transparency, and then plot 3 means parametric plot. This x is y is z. I multiply them by 2 to have a sphere of radius 1, which is a little easier to percept for human, and then we can label it appropriately. So I hope everyone is accepting this and can run this thing. Next step. So we do have these trajectories, these blue lines on a transparent sphere, which is great. It is good, but it is a little difficult to project dynamical procedure onto trajectories, especially if it is not one-dimensional, two-dimensional, if it is three-dimensional trajectory. So the script Rabbi wrote movie, it runs absolutely the same thing, but it has a couple of lines that modifies that are designed to focus onto dynamical aspect. So if we run this code Rabbi wrote 3 movie, you see there is a, at the top, it shows how time is accumulated. And then at the bottom, there is a red dot. At initial time, there is no change because envelope of electric field is 0. But when we arrive to the time when pulse is non-zero, our traveler along the globe starts a journey from South Pole to the North Pole, right? It's a little slowed down on my screen because it uses Zoom transmission and recording. But as we go through, it arrives very close to North Pole. Not exactly, because I did set up very, very little detuning from, so it's offset is very close to 0, but non-zero. So therefore it arrives a little bit apart from North Pole. And then it stays there unchanged for certain time because we stop irradiating system. Now, for a period of time, it is isolated. The envelope of electric field is 0, and system just practices postulate number, whatever, 3 of quantum mechanics, that isolated quantum system doesn't change its quantum state, either eigenstate or superposition of eigenstates. If it would be in Schrödinger picture, this red dot would also would rotate on the equatorial plane like crazy. But the main point of rotating frames that we avoid these quick rotations. Okay, now we do experience second pi pulse, and the system drops from the North Pole back to the South Pole. So, and it arrives quite close to the South Pole, and then the envelope drops to 0, and the system stays unchanged, and the red dot, the little traveler, just has some rest with penguins on the South Pole. So the time indicator at the top of the figure shows like 600. So in 600 atomic units of time for the parameters that have been chosen, we did experience 2 pi pulses. If we wait comparable time, there will be another pulse, and it will go again from South to the North Pole. So I think the rest will be repeating the same pattern, but there are additional lines in the code that do convert this dynamical simulation. They save each snapshot and create it in a form of the movie, of the animated cartoon that can be uploaded to YouTube. And as a part of suggested lab report / homework, I invite everyone to practice this code, which will generate the movie file, and then upload to YouTube and submit link to YouTube video as a part of your report. So let it keep running, and I'll go over the code that everyone feels comfortable and knows what and how to change. So the plotting part is inserted inside the loop over time. So the stuff that was at the end of the previous version of the code now is inserted right in the place. So it is replotted each time we recompute quantum state of the system. So we plot accumulated trajectory, this average SX, and at the same time we plot a single red circle at a point of the present value of SX, SY, Z. And then the time is plotted, labels are placed, a little pause is added, otherwise it will go too quick. And in addition, there are 3 instances in the code that generate the movie. So first instance is at the very beginning. So one opens file where the movie will be saved. If you want to do several movies with different parameters, just change the name of the file or name it after whatever you find reasonable. So open channel to save movie. Then after instant of drawing, one is getting frame and saving frame into this video channel. And at the end of the loop cycle over time, this video channel is closed. So this coding effort is expected to result in generating the video file that can be uploaded to YouTube. So let me check how are there any questions or suggestions or criticism, or it all makes sense? So please feel free to express questions. Okay, or vote as London did voted. So if there are any discomfort or something sounds strange, please do not hesitate. It's my responsibility to give comments in details.
So just to clarify, like this, what we're producing with the script is not the average ensemble case, or
so
it
yeah,
is?
This version of the script doesn't have ensemble average yet. It is still a single spin 1/2 or pseudo spin, like loom of a single molecule.
Okay.
We on the overall goals of our goal, on the train of how our materials are developed and arranged to each other, we will have at least 2 more stations. I hope more, but there will be 2 more stations. Next major station number next is how will this dynamics change if you perform an average over ensemble of the same spin 1/2 systems. If it is an ensemble of many spins placed nearby, and each of them have slightly different frequencies, slightly different pace of phase accumulation. So it's next station. It still will be reversible Hamiltonian quantum dynamics, but it will be average over ensemble. And typically the right words to speak about it is inhomogeneous broadening. The important station next +1, number 2, is what would happen if our spin is interacting with a substrate solvent environment and comes into thermal equilibrium. So the code that we are looking at now do not have ensemble average. They do not have inhomogeneous broadening. They do not have thermal equilibrium. Why we study the single spin with so much details? Because we want to learn trends, how the single spin or pseudo spin system responds to the external perturbation, to pulses, and then use this knowledge as a reference point for the leap, for the jump to next new material, to the next stages, to discover new phenomena. Because if we immediately jump to final answer, we will not recognize how important and what has been changed. So we need this preliminary step as a reference point. Caressa, does it make sense?
Overall, yeah, it's a little clearer. So we're not dealing with an ensemble average, so we are in thermal equilibrium currently.
Yes.
Okay. Thanks.
Yeah. Many thanks for the question. Okay, and sharing screen once again. So I believe, yes, there is no red button to stop. So it generated both trajectories of individual projections. Yeah, and the image, three-dimensional image is going. But I can go into YouTube channel, and I believe each of us who has a Gmail account is automatically a holder of a YouTube channel, so it is free. And let me maybe repeat things like Google. So YouTube, and then if I'm just going to YouTube, so it's some suggested videos to move, and then you click in the upper right the plus symbol and camera. Let me show it once again. Create. You see it upper right, create, and then it shows upload videos. And then you can identify select files with this little arrow, and then you navigate to the directory where you were running this script, and you identify that there is a movie file. So you click upload, give it some name. Tell that it is not for kids, and selecting, maybe you want to make it public or unlisted. Private doesn't work because then no one can see it. And then it does generate a link. So you can copy this link and share the link in the email or chat. I suggest you share it in the email, because it will be a little record and indication of of this in-class effort. So let me encourage everyone to practice this upload of the YouTube video and send. Do not wait. Send an immediate email with a link. So we can also do screen sharing if something doesn't work. But if I see your link with video that does work, then it will be the best way to prove that everything is healthy. So go into YouTube, and then it demonstrates this video. If the motion of this red point is too slow, one can change the pause parameter in the in the settings of the code. And I promise to put a like to everyone's video who will send it to me. So yeah, you see, it's basically the same thing, maybe a little quicker than it was in the simulation mode. You didn't saw it. Sorry, I was planning to share a screen. Let me do it over. So here is a working link, and to upload, one just goes into create, upload video, and then select the movie that has been created by the MATLAB. So please practice doing it. Sorry, I thought we go on the on the shared screen. Okay. So I believe main part of the program is done, and the only thing left is to check once again for any questions and make a most clear description of what is expected in the lab report. So feel free to stop me at any minute, and as if there are no questions, I will just speak a little bit about the lab report. Share screen. So right now the simulation was done for PyPulse, which promises 100% conversion from ground to excited. The invitation, the question for the lab report is to check if we change it from pi to pi over 2 to pi over 3 to pi over 4 to maybe 2 pi, maybe 4 pi. Well, it will be not interesting. Or so this can be done by adding a fraction, in just in Hamiltonian, or right after the definition of the field intensity. So just divide or multiply, then rerun the code, and copy paste the image of projections and upload the movie of Global Traveler. You will be pleased and surprised to see how things are changed. And I believe London was asking about intuitive understanding of what is going on with two-level system or spin. This little exercise will add and increase intuitive understanding of the standard behavior, time-dependent behavior of the spin system in the external field. So I believe I'm fully done with the program, with the plan for today. So I'm open for questions, and please try to run the codes and let me know if something is not working. I'm here to assist, and we can do these quick sessions of one is sharing screen shows to me, and I will assist in fixing things if something is not working. So please vote, please confirm if everything makes sense, and please confirm if the lab report assignment is something doable.
Yeah, I have a question. How do I download the video from MATLAB again?
Not download, but upload.
From MATLAB. Before I upload, like
Upload.
yes, like how do I extract the video from MATLAB?
Okay. So would you feel comfortable sharing your screen?
Yeah. Okay, you have to activate it. Said you've disabled.
Oh, okay. Just a second. Make co-host. Yes. Make co-host. Yes, I'll just make sure that everyone is co-host, just in case sharing screen is needed. So I believe everyone is co-host, so yes, let's go ahead and sharing.
Okay, so this is it. This is the video after.
So,
yes.
Patricia, which code? Oh, okay. So, did you run LAB3 movie?
Yes, this is it. After it has.
Okay.
Yes.
Okay. So, let me request remote control, if you permit.
I have.
Okay, thank you. And now, we can either type PWD, or we can look on the panel here. So it shows drive C, directory users, subdirectory HP Elite Book, subdirectory downloads. So it is a location of your let's do it less star.avi. Oh, you have a lot. So you do have block movie 1 MP4 AVI, right?
Okay, in my downloads.
In your directory downloads. Now,
Oh.
will you just bring up the browser?
This is it.
Just bring it up so that we can see it. Share the whole, maybe stop. Okay, yes. Okay, now click create. Upload videos. Yes. And exactly, yes. And if you want, you can give a little explanation, because you have several movies, so you can type the sequence of
Okay.
by pulses. and then go ahead and scroll, and it will ask a couple of questions just by the rules of YouTube. So nothing wrong is tell that it is for kids, but then it will have additional questions. Playlists. It's like a folders of organize.
So, Dr. Keeling,
Yes. If anyone feels ready and everything is clear, feel free to disconnect. There will be no new material and only to answer questions. Yes, Hadassah.
So do you want us to send you a link of a video earlier to indicate things are good, or are we okay to just send the links to our videos once we have it all done in the report?
You can send link to one video right now as an indication that everything is clear, and you can do it. Then on your own schedule within a week, just send a lab report.
Okay.
Make sense?
Yep. Thanks.
Yeah, thank you. So Patricia, it will take, as you see, about 10 minutes, and then maybe another 10 minutes to process video, and then it will be available, but you can send link right away.
Okay. Thank you.
Thank you. So if your question is done, you can stop sharing. Okay, so please feel free to express any questions, concerns, and request for assistance. I'm very enthusiastic to do it if needed.
So mine says processing abandoned.
Please repeat what it says.
Processing abandoned. Like this video could not be processed.
Okay, would you please share screen? Oh, yes, yes. Let me ask for remote control. So you are trying to upload the MATLAB code, right? And the MATLAB code, RABI-RO3.m is not a movie, it's just a code, it's a script. So you need to use this one that ends with extension telling that it is a video file. Right now it has 0 kilobytes. Maybe the simulation hasn't been finished yet. So let's see what is going on.
It's open. Let me just
You can temporarily cancel upload. And would you please bring up the movies and the command line of MATLAB? See, it shows time 600, so it will run until about 2000. And to upload, you need to wait until the finish of the movie. Before it is done, movie file is 0 or it is being accumulated.
Okay. Thank you.
Thank you. And I'm confident it will work. Yeah, thank you for bringing it up. Any other questions or suggestions? Lori, did this movie work for you?
I think so. I just sent you an email with a link.
Okay, I look forward to check emails. Thank you. Adam, do you feel comfortable with everything?
Yes, I think so, yeah.
Okay, Yep. I'm in the middle of the process of sending materials for presentations. I'm not yet done, but hope very much to complete it during this night. So if anyone didn't get suggestions or materials, I plan to send something. Okay, so everything is done. Feel free to disconnect. If you want to chat about anything, feel free to stay, but it is not required. The program of the lab number 3 is fully accomplished.